Greetings, everybody, and today we have a guest professor. This is Professor Ninja Meows. Okay, he's not teaching, he's going to take a nap. I guess that means I have to teach this class. What are you going to do? So, we talked a little bit about this before, but in order for us to talk about the sun and how it works, how stars actually generate the energy that they do and shed light into the universe and so on, we need to define a term. And that, of course, we've already talked about, but this is called hydrostatic. You know what? That's supposed to be an R. Hydrostatic equilibrium. Uilibrium. Now, we talked a little bit about this before, but essentially, hydrostatic equilibrium is when you have a balance, say, in the core of a star, right? Here's the star and there's the core. There's going to be a balance in between the force of gravity pushing on it and the energy that it is generating, right? And so gravity's pushing in and the energy is pushing out. And this finely tuned balance in between these two keeps the core in its structure, right? If it radiates too much energy, it expands and it loses the necessary amount of temperature and pressure in order to continue to generate energy, right? And so it kind of has its own feedback. If it generates too much energy, it expands and then it loses its ability to create energy and shrinks back again, right? And if gravity overcomes, then the pressure increases, and just very much like a pressure cooker, it's going to generate more energy as a result, right? It's going to generate more temperature, and it's going to cause more thermonuclear reactions to occur per unit volume. And so there's this kind of feedback cycle that's keeping it at this perfect size and state. Okay, so the outward pressure by the energy generation is equal exactly to the gravitational force. Also, the outward energy pressure is exactly equal to the amount of energy that the star gives off. If this were not the case, then essentially the star would be like a giant battery and it would just keep storing more and more and more energy, and then it would just get bigger, right, and pop or something. But stars don't do that. No, instead they live for at least millions, but usually for billions of years, shedding energy all the time, every day, right? And so the amount of energy that it gives off at the surface has to be equal to the amount of energy generated at the core. So the amount of energy generated by the core equals the amount of energy radiated from the surface of a star like the sun. Okay. How much energy is that? Well, it just so happens that it's quite a tremendous amount, and we talked about this sort of briefly before. If you look at our friend E equals mc squared, we generate a lot of energy by turning a little bit of mass from hydrogen into helium because of this c squared factor, right? Essentially converting 1 gram of hydrogen to 1 gram of helium releases enough energy that it's like 10 of those bombs. We talked about that before, so it's a lot. Now, because we know how much energy the sun is radiating, right? We know how bright it is, we know what its surface area is, and so we know the total amount of energy that it's giving off. If we compare that to E equals mc squared, we should be able to figure out the mass of energy, or the mass, of fuel that it's burning for energy in its core per unit time. And essentially, because we know the amount of mass energy difference, the amount of nuclear binding energy in one helium atom, right, and we compare that to the mass of 4 hydrogen atoms, we can figure out how much energy the sun can give off before it burns up all of the hydrogen in its core. And if we compare that to how much energy it's giving off per unit time, like every second of every day of every year, right, we should be able to figure out how long the sun has before it burns all that out. And that's actually pretty straightforward because of, Albert Einstein, right? And it turns out that the sun should live to be about 10 billion years before it burns up all of the energy in its core. Sounds like a very, very long time, but most likely we've already probably been around as a solar system for about 4.5 billion years or so. So it's used up almost half of its lifespan. Okay? Now, in order to try to explain how it is that we take 4 hydrogens and smash them together to make a helium atom, you have to know a couple of things, and the first of which is that even in a star like our sun that has 99.99% of all the matter in the solar system and has a mass of 2 times 10 to the 30 kilograms, which is a whole lot of hydrogen and helium, even at that size and scale with all of that gravity, right, all that gravitational force and all of that outward pressure, even with all of this stuff going on, it's not enough in order for there to be enough heat to directly take hydrogen and smash it together and make helium. And so we have to introduce quantum mechanics in order for this to work. Some hotter stars undergo different processes, different procedures, but stars like our sun have to do things like this thing that we call the proton-proton chain. Now let's talk just a little bit about this proton-proton chain, what it is, what it does, how it works. Sometimes we just call this, that's a proton to proton, right, connection, so proton-proton chain. Okay, and if we want to look at the proton-proton chain like a chemistry equation, it makes a little more sense, right? Of course, in order to talk about the proton-proton chain, we need to talk a little bit about the 4 fundamental forces in nature. Okay, there are 4 of them. There's a nice diagram, I think it's like the 6th image in today's bank, that shows when these forces kind of appeared out in our universe, at what time after the Big Bang they appeared. And basically after like a microsecond after the Big Bang, like a millionth of a second, all the 4 forces had emerged from that one single primordial force. There are 4 of them. There's gravity, obviously. That's been a big one. There's also this funny thing called the strong nuclear force, right? Now, if you remember, if we want to look at, say, the cross-section of like a helium atom, here there are 2 protons inside the nucleus. Protons are both positively charged, and if you remember, opposite charges are supposed to attract and same or like charges are supposed to repel, right? Like aligning the two ends of a magnet, right, against each other or aligning them straight towards each other. So here we have two neutrons, right? Helium also usually has two neutrons in the stable helium-4 nucleus. Then out here is like an electron, and then out here is another electron down in the first spherical orbital. This is your basic helium atom, right? Now, if these two charges are positive, they should repel each other, right? So how can they live right next to each other inside the nucleus of an atom? Well, there's this thing called the Yukawa potential, named after the Japanese scientist who discovered it, that shows essentially that when these particles get close enough to each other, there's this sort of potential, this force that holds them together. We call that the strong nuclear force. The strong nuclear force only accounts for so much, however, and so for more massive atoms to stay stable, you need to have more of these neutrons in them to sort of act as a buffer in between all of the protons. Okay, so that's gravity and the strong nuclear force. Also, there is a weak nuclear force, right? Like what attracts the protons and the electrons to each other. And that, of course, is what dictates where these electron energy levels are going to be. Obviously, they would be at different distances, right? You'd have different shaped orbitals if this was a hydrogen atom with only one proton in it, right? But also, if there's like another electron out here, these two should repel each other, right? So this is what we call the weak nuclear force. And it's very similar to this other idea we had where if you have two like charges, they should repel each other. We call it the electromagnetic force. Sometimes, we like to kind of say that they're the same. Obviously, before 1 microsecond after the Big Bang, they were one force, right? And so we called that the electroweak force. Nowadays, there are independent charges that are outside of atoms, right? And so, we have like currents or whatever, things like that. And so we call the electromagnetic force different, even though they basically run on the same principles of electricity and magnetism. Okay, so now that we know a little bit about the four fundamental forces of nature, we have the strong nuclear force that holds the nuclei of atoms together. We have the weak nuclear force, the interaction between the charges. We have gravity, of course, and we have the electromagnetic force. Right, the four fundamental forces of nature. Now, in order to understand how the proton-proton chain works, by the way, there's an image of it. I think it must be the 11th or something image in today's image bank. Something like that. If you want to look at the proton-proton chain kind of as a chemistry equation, it kind of makes a little more sense, right? Okay, so if we look at this proton-proton chain, we're going to start with 4 hydrogens, and at the very end, we're going to end up with 1 helium atom, 1 helium-4, right? We're only going to have one of these. Actually, this doesn't even need to be here, right? This is just one helium-4. Actually, this doesn't even need to be here. We know what a helium atom is, right? Okay, so actually, you know what? I'm just going to put the 4 superscript there. Okay. Now, there are a number of ways that subatomic particles can interact with each other. And one of them is this funny kind of interaction where you have essentially a proton that collides with another proton. And what happens after they collide is you end up with a proton and a neutron. Now, protons are positively charged, neutrons have no charge, so that positive charge had to go somewhere else. And that leaves in the form of what we call a positron. It's the antimatter particle of an electron. If an electron and a positron meet each other, they annihilate each other and release a ton of energy, right? E equals mc squared. But also, because we have to observe parity in lepton number, we also emit a funny particle that we call a neutrino. Okay? So what's going to happen here is, if you look at the top and the bottom, we start with two separate reactions where we take hydrogens and we bang them together. And what happens? Well, we end up, instead of just with, two hydrogens, we end up with two deuteriums, right? Which is that's helium-2, right? Or hydrogen-2, sorry, heavy hydrogen. It's hydrogen with an extra neutron. And in so doing, we're also going to end up with, we're going to end up emitting two positrons and two neutrinos. And in all likelihood, these positrons aren't going to live very long before they collide with electrons somewhere, and so those are going to give off some gamma rays. We'll say each one gives off 2 gamma rays, because one for the electron, one for the positron, so we're going to give off 4 gamma rays. Okay? I'm sorry. We ended up now with 2 heavy hydrogens. Okay? Oh, by the way, the stuff that goes into a chemistry equation and the stuff that comes out of it, we call these the products, and we call these the products and these the reactants, right? So for our first reaction, we smashed 4 hydrogens together. Actually, we haven't even gotten around to the helium yet. And we ended up with 2 heavy hydrogens. We had 2 positrons, but those got destroyed or annihilated by electrons, and those emitted 4 gamma rays, and we also ended up with 2 neutrinos, right? Okay. Now, our next reaction, we're going to take 2 more hydrogens, and we're going to smash them into these 2 heavy hydrogens. Now we've got productants, reactants on both sides again, so we're just going to get rid of them. So now we're talking about smashing 4 hydrogens together. What do we get this time? Well, when you take your heavy hydrogen, right, you got a proton and you have a neutron, and you smash a 3rd hydrogen in there, right, your 3rd proton essentially, because hydrogen atoms are just 1 proton, 1 electron. You smash another one in there, and essentially you end up with this. This has 2 protons in it. That's a helium, right? But it only has 1 neutron in it, so you end up with 2 helium-3s. Right? Okay. Now, because there's a certain amount of momentum in this collision, this is also going to give off some energy in the form of 2 more gamma rays. I'm just going to move this up here. So I'm going to say 6 gamma rays now, right? This is how much energy is given off, essentially. That's a lot. Okay. And now we're going to take these 2 helium-3s, and we're going to collide them together. And now, since we've got it on both sides, we're just going to remove them. Okay. So what happens when you have 2 helium-3s? That's a proton, and a neutron, right? That's one helium-3 atom, and then we're going to crash another one into it. Proton, proton, neutron. These are all going to smash together. Okay, now the outcome is going to be that we get two helium-4s. Okay? Now a helium-4, I'm sorry, we're not going to get two, we're just going to get one. I can count, I promise. So we're going to get 1, 2, 3, 4, 4 protons in total, right? And then 1, 2 neutrons. But a helium-4 atom, right, we're going to combine these two, and what we're going to make is 1 proton, and 2 neutrons, right? Neutron, neutron, proton, proton. But that also means, so that means we're going to take that one, that one, that one, and that one, and we're going to end up with 2 protons, right? Or 2 hydrogen atoms. And so we smash these two helium-3s together, we get a stable helium-4. Helium-3 doesn't live that long, you know, unless it crashes into something else. And fortunately, it doesn't have to live very long because, remember, you're talking about the core of a star where there's this intense amount of gravity and pressure, right? The density is really, really high. Particles are banging into each other all the time. And so this helium-3 doesn't have to live very long before it crashes with another helium-3 and makes a stable helium-4. Now those 2 protons are going to get spit out and essentially just be hydrogen atoms. Now we've got hydrogen and hydrogen here, so we can just cancel those out. And essentially, what we end up with is we start with 4 hydrogens and we smack them together to make 1 helium. And in so doing, we release a ton of energy, tons of gamma rays, really high energy, right? And some neutrinos from the beta decay events. Crazy, right? So we started with 4 hydrogens, we made a helium, and released a ton of energy in the process. That is how low-mass stars like our sun are able to give off a ton of energy by taking hydrogen and making helium. That's how it's done. Obviously, the story is going to be somewhat different for larger, more massive stars, but for this one, not so much. Okay. Now, if this is what's actually going on inside the core of a star like our sun, then we should probably know how many reactions are going on per unit time, since we know the amount of energy that's being released. And that means we should know how many neutrinos, how many of these tiny little, almost massless, completely chargeless particles are being released per unit time. And if we take that, you know, if you want to divide that evenly amongst the surface or whatever, we should be able to figure out how many neutrinos are passing through, say, the Earth, or a certain, you know, surface area here on the surface of the Earth per unit time. It turns out that it should be a whole lot. If we're just going to compare the amount of neutrinos generated in the core of the sun per unit time, we should be able to detect, you know, a certain amount here, even on the surface of the Earth, as small as we are. We should be able to detect a certain amount of neutrinos per unit time. And so we built detectors, and we were right. We found a lot of them, but not as many as we thought. We called this the solar neutrino problem, and for a long time we thought it was, you know, an issue, that maybe we didn't understand how things worked, but once we realized that neutrinos are really, really kind of funny particles, and they oscillate in between their own states of being, right? They oscillate in between the different neutrino types. There are electron-type neutrinos, muon-type, and tauon-type neutrinos, plus their antitypes, and so on. that neutrinos just kind of oscillate in between their own various states. And so if you set up a detector to detect, like, one type of neutrino, it's not necessarily going to read the other ones. It's a lot more difficult. It's a different kind of beast to try to detect a tau-on as opposed to a muon, right? And once we figured that out, we realized that the solar neutrino problem was not actually a problem, and that we had actually solved it. This oscillation in between the different types of neutrinos is due to this thing called the Higgs boson field. And if you remember, just a few years ago, we discovered the Higgs boson, which is this field, this theoretical energy field that gives mass to matter. And our discovery of the Higgs boson, which is this kind of intermediary particle, this intermediary state, which is why they're calling it the God particle, is because of our understanding of this Higgs boson field that we were able to puzzle out that neutrinos change in between their different types. So incidentally, human beings are pretty smart. We figured out nuclear physics, particle physics, quantum mechanics, theoretical astrophysics, or how it is that stars form and generate energy, gravity waves from relativity, neutrinos, and those are only the things that we've talked about so far today. Pretty good, right? Okay. Now, if energy is generated inside the sun, we want to look at kind of the profile of the sun. And if you look at if you go back to the first few images in today's image bank, the core is the smallest part, right? It's about, the 10% or whatever mass in the middle. And then out here is kind of like the upper edge, right? And then out here is the atmosphere or whatever. Excuse me. Obviously, gravity is going to be stronger here in the middle, right? And that's also where the greatest amount of energy density is. Here towards the surface, gravity isn't quite as much, right? And so the energy density, because here there's more energy per unit area here, and then out here it's like more spread out, right? The innermost part of the sun, maybe about 10% of its mass, maybe about 20% of its radius, that's where the core is, right? Obviously that means that down here in the core is where obviously the greatest gravitational force is, right? And that means the most pressure is going to be there. That means also that it's going to be much more dense in material than the rest. But that also means that in order for it to stay in hydrostatic equilibrium against this great amount of gravitational pressure, there also has to be an equal amount of energy pressure, right? Force per unit area, in order for it to stay afloat against its own gravity. And that also means that more or less all of the energy that is produced by the sun is produced in this core, right? If our theoretical models are right, and they have been so far to a almost unnerving degree of accuracy, that means that all of the sun's energy is generated here in the core. Now, if energy is generated there in the core, and here at the core, matter is really, really dense, right? You can imagine if you were, say, one of these hydrogen atoms or whatever that was here in the core, okay? So let's say you're this hydrogen atom, right? And you absorb just the right amount of heat, right, so that your electron jumps up one energy level, and then as it jumps back down, it emits a photon equal to that energy transition, right? Now let's say we wanted to track the progress of this photon. How far does it go before it runs into another atom and maybe excites this electron up and then gets excited back down and re-emits the photon in a different direction, in a random direction. Well, it's probably not going to go very far, right? Because the core is, like we said, it's crazy dense in material. We're talking about hundreds of thousands of kilograms per cubic meter, right? That's a whole lot of hydrogen or helium gas. It's super dense. And so if it's going to take a certain amount of time for this energy to get absorbed and then re-emitted and absorbed and then re-emitted, it's going to take a little bit of time, especially if it's getting randomly redirected. It might go this way and then that way and then back towards the core and then back towards the surface and then this way and then that way and then back towards the core and then this way and that way and then back towards the surface. And it's going to be random, right? Because the direction that you're going to be emitted depends on, where the atom is facing, basically, right? So, if you're going to be emitted randomly, theoretically, over the course of time, you will make it to the surface because matter is less dense at the surface than it is at the core. So let's say you get emitted, like 1 billion times or whatever. Every time that you get emitted toward the surface, you're going to go a little bit farther. The average distance in between particles, what we call the mean, it's supposed to be m. Let me just write this better. The mean free path. The average distance that's open, that you're actually going to be able to go before you get absorbed by another hydrogen atom or whatever, and then re-emitted again, that average distance is greater towards the surface. So if you get absorbed and re-emitted 1 billion times, every time you go towards the surface, you're going to make just a little more progress than if you got re-emitted towards the core, right? And so over the course of time, you may get absorbed and re-emitted, absorbed and re-emitted, whatever, but eventually you'll make it to the surface. And then you'll get emitted, maybe you'll get absorbed by the atmosphere, maybe you'll go straight through, whatever. And then, you may get reabsorbed by the atmosphere and reabsorbed, and eventually you'll make it out of the star. Now, if you had to guess how long it would take for a photon, remember these travel at the speed of light, to go from the core to the surface of the sun, how long would it take? Some basic relevant information. The radius of the sun is something like 7 times 10 to the 8th meters, something like 700,000 kilometers. And light travels like 3 times 10 to the 8th meters per second. So if it was going to go in a straight line, it would probably take, a little over 2 seconds. But it's not going to go in a straight line. So how long should it take? Well, that is a question, isn't it? At this time, I'd like you to think about it for a second, maybe hit the pause button and take a guess. Normally what I do is I have everybody vote on what they think as a class. But the actual figure, the average time that it takes a photon generated in the core to making it to the surface and escaping the sun is something like 100,000 years. So, all of the light hitting us from the sun was generated a long, long time ago. Way before any of us were born, before there was human civilization, before there was recorded history, probably before we mastered fire and the spear, definitely before the wheel, right? as a species, we've probably been around maybe 200,000 years. That's as far as we find our species in the fossil record. So it takes 100,000 years for a photon generated in the core to make it out to the surface. But it only takes 8 minutes for that light emitted from the surface to get to the Earth, some 150 million kilometers from the surface of the Earth. 150 billion meters, whatever you want to call it. Okay. The core of a star like our Sun is something like 15 million Kelvin, really, really hot, which is, that's like 15 million degrees C. And it's dense all the way up until about this point, where we call this the radiative zone, which is more like 100,000 Kelvin. At this point, you have like convection currents, right? The actual gas, the hydrogen and helium gas, makes convection currents, and that takes it to the surface. And so really, the bouncing around happens the most below that point, right, where the density of the Sun is its greatest. At that point, of course, convection takes over. Now, that's what we think is going on inside the core of, and every part of the volume of the Sun below the surface. And in order to try to test that, well, we can't exactly set up seismic monitoring stations on the surface of the Sun and track seismic waves through the Sun, right? So we can't do what we did here on Earth to try to figure out what the interior properties are like. However, fortunately, the Sun is not made out of rocks and metals and things that we can't see through. This is all gas, right? Especially here at the radiative zone. We can track its movements pretty simply by looking at the Doppler shift of the material. And as a matter of fact, we can see pretty far down into the surface. Not all the way directly to the core, that's much trickier, right? But we use what we call helioseismology by tracking the Doppler shifts of portions of the surface of the Sun all the way down into its depths in order to verify that, yeah, it gets denser the further we go. And there's only convection here at the surface. And so our model, our physics, right, our understanding of how this is supposed to work according to gravity and electricity and magnetism and the nuclear forces and theoretical astrophysics and quantum mechanics and nuclear physics and all that stuff, it works. Okay, that's enough for today. We'll pick it up next time with the second half of Chapter 11. Please contact me if you have any questions, and I hope you've enjoyed this video. I'll see you next time.